Welcome to the third part of the introductory practical for the FSL course. Here we're going to look at some miscellaneous command line utilities, collectively called FSL utils. To start with, we'll go back to the place where we've stored the data that we're playing with. So that's in this particular location. And this is where we left it before, after we did brain extraction. And that's common for things which come straight off the scanner. That's how they're reconstructed. And then there is some other information at the bottom, which is just about how to display the image in the display tool, such as fossilize. If I look at a different image, so now let's look at Thresh ZStat1, then you can see that it's a 64 by 64 by 21 image with 4 by 4 by 6 millimeter voxels, which are huge. This is quite old data. And this one is now stored as float 32, which is common for most of the analysis outputs, because we want to store values like a Z value of 3.2, for instance. There's also another tool called FSL HD, and that gives us the full information of everything which is stored in the header of these files, which are nifty files. So if we run that on this file, then we actually get all of this information. So we can see everything which has been spat out by that command starts here, so it starts with the file name, and then we've got the information about the size, but continuing on to higher dimensions, which we normally don't use, but occasionally are used in some more advanced analysis pipelines, and then all sorts of other information about how it was scanned with respect to some of the directions of the axes and the coordinate information. Most of this you won't have to know. Occasionally we'll talk about little bits and pieces of it as we go through the course.
Okay, the next tool that we can use is called FSL Stats, and that's a general tool for looking at some of the statistics or values that are in the image. So it's quite flexible, and there are quite a lot of different ways in which you can use it. And to get those ways, you can always type FSL Stats by itself and hit enter to get all of the options. What we're going to do here is just have a look at the range of the values that are in the image, and we're going to do that by including the flag minus capital R and also minus lowercase r.
So if we run that, then we get 4 different numbers output. The first 2 are related to the minus capital R, which if you look in the list of the different options here, is actually giving us information about the minimum intensity and the maximum intensity. So that's the minimum intensity in this image is 0, the maximum is 3767. If we look at the minus little r, then that gives us information about the robust range. And so again, it's 0, but now it only goes up to 16,711 and a bit. That's useful because it tells us about the intensities which cover most of the voxels in the image. There are only a few voxels which are outside of that range. In this case, we did 2 different options. We didn't have to. We could have just done one. So if we did just minus little r on its own, then we would just get these 2 values. And you can combine as many of these options as you want together in a single command. Okay, now let's look at a different option in FSL Stats. So if we have a look at the range of options, then there are lots of different things that we can do with FSL Stats. But one of the other quite useful ones is to calculate a mean intensity. So for instance, if we did FSL Stats, a high-res image again, minus little m, that would give us the mean value over the whole image. If we did with minus capital M, then we get the mean value of only the non-zero voxels. So these values are very different. You can see that the first one is just under 2,000 and the second one is about 12,000, which if we have a look at the actual image in Fossilize, we can see why that is. So here you can see that if I click around inside the brain, then I'm getting values that are, around, in the region of sort of 9,000 through to about 15,000, say. Whereas outside is all zeros. So what we've got with these two options here is that we've got a mean value which takes into account all of the zeros as part of the calculation, and so the average value across everything therefore is quite small by comparison with the average value only within these brain voxels, excluding everything in the area outside. And then that value just inside the brain has an average of 12,000, which is more consistent with what we're seeing here. Depending on what you're doing, you might want one option or the other. In a similar way, you can also calculate the volume of an image. So I could do FSL stats, rs minus little v, or capital V. And again, this is doing it either across every single voxel in the image, so that's actually a count of the voxels in the image, or this is a count of the number of non-zero voxels within the image. The second value here is actually that same volume but converted into millimeters cubed by taking into account the voxel size of this particular image, which, if we have a look, happens to be 1 by 1 by 1.25. So there would be a factor of 1.25 between these two numbers.
So now we can move on to another command in the FSL utils that we can use commonly, and that's FSL maths. So first of all, we can type FSL maths and just have a look at the different options. And this is a very long list because there's lots and lots of different things that you can do with FSL maths. But essentially, it is a tool for doing simple calculations on images. And so we're going to look at a few examples of this. The first thing that we're going to do is actually subtract one image from another image. So we will start with the command FSL maths, and then the first input is the actual input that we will start off with, and then we will subtract the second image that we will enter into this command line. And then the last input here is the name that we want to give to the output of this subtraction.
So unlike a lot of commands that you'll run across, this one actually reads from left to right and does things in that order. Most commands don't work that way, but FSL Maths is an exception, and it acts as a very general calculator. So now let's run that, and then we can have a look at the difference. So this is the difference between two of the images which we used before. So that's image 1, that's image 0, so you can see that they're very similar to each other. Now if we look at the difference image, then we only highlight a few areas where we've got sizable differences, and most areas have quite small differences. If you look at the actual values there, you get a sense of how big they are by comparison with the size of the values that you have here in the original images.
Okay, another thing we can do is to actually change this difference image into a percentage change image. And so for that we can use FSL Maths again. And in this case the input to the command would be the output that we've just created. And then we're going to divide that by the original image and multiply that by 100. And again, the last entry into this command is the name that we want to give to the output image. So we can load this into Fossilize to have a look at the difference between the actual difference image and a percentage change image.
Okay, so the image itself actually looks quite similar. So if this was our original imdiff, just the difference image. This is our imdiff percent, but you'll notice that some areas have actually changed in terms of how they look, but the main thing is the actual values themselves. So we can look at different areas and you can see the values for the two different images are quite different from each other, where the one for the imdiff% is now actually converted to a percentage change in intensity between these two different images.
Note that if we have a look at the command again, here we multiply the result of the division by 100, but you can also enter an image into this multiplication. So for each of the actions that you do within FSL Maths, you can either use integer numbers or you can use images.
Yes, so for instance in the first part here, it was dividing voxel by voxel, the different values, and then later on everything got multiplied by 100, all voxels.
Okay, so the last step that we can do now is to combine the two different tools. So we can combine both FSL Maths and FSL Stats. And the way we are going to do this in this scenario is to look at a mask image and create a binarized mask. So the first thing we're going to do is open an image in Fossilize and open a background image to overlay that on. And as you can see, this image contains values that range from 0 to 1. So this is a probabilistic region of interest that we've seen already before when we were looking at atlases. And what we want to do now is to create this into a binary mask, which contains either zeros outside of the ROI or ones inside of the ROI. And we're going to use the FSL Maths and FSL Stats tools to do that.
Okay. So let's start by taking this mask, which at the moment does not have binary values. It has some values which are in between, as we saw at some of these voxels. They have values of, say, 0.3 here, and turn it into a binary mask. So FSL Maths has an option for doing that. We need to type the name of the image, which is that. It doesn't matter whether you put the NIGZ there or not. I've been generally removing it, but it would be happy with if you left it there. And now we're going to threshold it, and so that's this option here, minus THR, at 0.5, which is going to make everything less than 0.5 equal to 0. And then we're going to binarize it, which is going to make everything which is non-zero equal to 1. So at the end of those two operations, we've got values which were up to 0.5 now ending up being at 0, values which are greater than 0.5 ending up being at 1. And then after that we're just going to save out our result with a new name. So I'm just going to put bin at the end. So often when you see bin, it'll mean binarized rather than throw in the rubbish. Okay, so now that's run, let's actually load that result. So here it is. And let's make that a different color. So let's go with the blue color range. And if I turn just that one on, then you can see that it's just a uniform color. And if I go around the voxels, everything is either 0 or 1. If I turn on the one underneath, then you can see that there are a few ones which are poking out here. The values of those should all be less than 0.5 because otherwise they should have been included in the 1. If I make the top one slightly opaque, then we should be able to find ones which were of a value which was not equal to 1 in the one underneath. So if I turn that one off, for instance, you'll be able to see that there are some values like that which are at 0.8, but that's actually become a value of 1 in our final mask here. That's one of these blue voxels. Okay, so now we're going to use this new binary mask to actually do something with the image.
So the next thing that we're going to do is to use this binary mask that we've just created in order to actually have a look at some results images that we are uploading now. So we're loading in the thresholded ZStat image into Fossilize to just have a look at it. But we'll go back to the terminal in a minute and actually use the binarized mask to get some summary results of this thresholded statistical image.
So here's what the thresh z-stat looks like. It's the same thing that we looked at before, and we can see how that relates to our binary mask here. So that's the one that we had, and you can see that there is some overlap with those two.
Okay, so now we're going back to the command line and we're going to use FSL stats to get some summaries of what is happening in the statistical thresholded image inside our binary mask. So the first thing we're going to do is a command that you should recognize from before, which is actually to just look at the volume of the mask itself.
Okay, so as we said before, the first value is the number of voxels and the second one is the volume in millimeters cubed. So because these are quite low resolution images, each voxel is quite a lot bigger than 1 millimeter cubed, so there's quite a large factor involved there. And it says that basically our mask has 75 non-zero voxels in it.
So the next command that we're going to run is to use the mask to and apply it to the thresholded z-stat image, and then to get the volume of the resulting thresholded image. So here's what the command looks like. The first input is the z-stat image. Minus k means that we're going to mask it by the next input, which is our binarized mask, and then minus v is the same as before.
And so now that you see we have a value of 26, which represents the fact that not all of the voxels overlap, which is what we saw when we were looking at them in fossilized a second ago. So now we're going to do the same command, but now we're going to use minus capital M, which is going to calculate, as I did before, the mean value across all of the voxels which we're including that are non-zero. And so that's actually going to be the same voxels which we were calculating the volume with above here, so it's across those 26 voxels only. And so now we have a value of 3.45, and this input image was in terms of Z statistics, and so that means that that is our average Z statistic value across those voxels which overlap between our mask and our thresholded activation. So that's just an example of a few of the things that you can do with FSL utils. FSL maths and FSL stats are very, very useful tools which it's good to get familiar with and to be able to use in general. There are other useful tools as well, and you'll find that there are optional parts of the practical that you can have a look at on your own. But this should be enough to get you to the point where you can explore that for yourself. And obviously when you get to the course, there'll be lots of other things that you'll be learning, and you can ask any questions that you've got on any of the material that we've covered so far. So we look forward to seeing you on the course. Bye!
Bye!